Right now, as you lie still in the dark, the room around you is being gently stretched and squeezed. You cannot feel it. Nothing can. And yet it is happening. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest revolutions in the history of science, the discovery that space itself can ripple, that the universe has been sending signals across billions of years, and that we finally, after a very long wait, learned how to listen. If this kind of wondering helps you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. Space is not empty in the way we tend to imagine it. It is not a blank stage on which things happen. It is something more like a fabric, woven together with time into a single, continuous surface that bends and curves and, under the right conditions, trembles. This is the picture Albert Einstein gave us in 1916. He called it general relativity, and at its heart was a quiet, radical idea that gravity is not a force reaching across empty space. It is the shape of space itself. Mass curves spacetime, and curved spacetime tells mass how to move. Think of a still pond at night. If you trail a finger slowly across the surface, the water responds. Ripples spread outward from the disturbance, carrying the memory of that motion across the water. A massive object moving through spacetime does something like that. Not on a surface of water, but on the fabric of space and time itself. The disturbance spreads outward in all directions, quietly, at the speed of light, roughly 792 kilometers every second. Einstein called these disturbances gravitational waves. And then, almost immediately, he doubted they would ever be found. He believed they would be real. The mathematics was clear, but the universe is vast, and the ripples, he thought, would arrive so faint, so impossibly small, that no instrument could ever feel them. For nearly a century, he appeared to be right. Gravitational waves have one quality that makes them unlike almost anything else we know of. They pass through everything. Light can be blocked. It scatters off dust, gets absorbed by gas, cannot penetrate a wall or a planet or the dense heart of a collapsing star. But gravitational waves move through all of it, through rock, through iron, through the full depth of the Earth, without slowing, without bending, without leaving any trace. They are passing through you right now, as they have been passing through every living thing that ever existed on this planet. We simply had no way of knowing. To understand what finally changed, it helps to picture what produces a gravitational wave strong enough to detect. Not a gentle disturbance, something almost beyond imagining. About 1.3 billion years ago, long before the first complex life appeared on Earth, two black holes were circling each other in the dark. One had a mass roughly 29 times that of our Sun, the other about 36 times. For millions of years, perhaps billions, they had been spiraling slowly inward, each orbit drawing them a little closer, each revolution sending faint ripples outward through space-time. And then, in a fraction of a second, they merged. Two black holes, each containing the compressed remnant of a dead star, collided and became one, a single black hole of about 62 solar masses. The remaining mass, roughly 3 suns worth, did not simply vanish. It was converted entirely into gravitational wave energy and released in that single, brief moment. In that fraction of a second, the merger radiated more energy than all the stars in the observable universe combined. Every star, every galaxy, every quiet sun burning in the dark across 93 billion light years of space. All of that light, all of that warmth, all of that slow nuclear fire outshone in energy by a collision that lasted less than a heartbeat. And the ripple from that collision began its journey. It traveled for 1.3 billion years. Through the expanding fabric of space, through the slow drift of galaxies, through the long dark between stars. It passed through nebulae where new suns were forming, through the outer edges of spiral galaxies, through the vast, quiet voids between galaxy clusters. It arrived at Earth on the morning of September 14th, 2015, and something was waiting for it. LIGO, the Laser Interferometer Gravitational Wave Observatory. It is, in some ways, the most sensitive instrument ever built by human hands. LIGO has 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. Each detector is shaped like a capital L. Each arm of that L is precisely 4 kilometers long. Inside, a laser beam is split and sent down both arms simultaneously. The 2 beams travel to mirrors at the far ends, reflect back, and recombine. Under normal conditions, they cancel each other out perfectly. But when a gravitational wave passes, when space itself is stretched along one arm and compressed along the other, the beams no longer cancel perfectly. A faint interference pattern appears. The displacement LIGO is designed to measure is about 1,000th the diameter of a proton. A proton is itself roughly 1/1,000,000th of a nanometer wide. 1,000th of that. It is a number that resists intuition. It is smaller than anything that has a name in ordinary experience. And yet that is what LIGO was built to feel. On that September morning, the signal lasted less than 0.2 of a second at the detectors. A brief upward sweep, a chirp. Scientists would later call it a rising tone, almost musical, almost nothing. It was the sound of 2 black holes becoming one, arriving after 1.3 billion years of travel, compressed into a moment shorter than the blink of an eye. Einstein had predicted this in 1916. He had doubted it would ever be found. And on a quiet morning in the American landscape, 2 machines of extraordinary stillness finally felt it pass. Space had rippled, and for the first time in the long history of this planet, something had noticed. That morning, 2 machines registered the same signal. Not one machine, 2. The first sits in Hanford, Washington, a quiet stretch of high desert in the American Northwest, flat and spare, the kind of landscape that holds stillness well. The second sits in Livingston, Louisiana, a different world entirely, humid and green, surrounded by pine forest. Between them lies roughly 3,000 kilometers of continent, roads, rivers, mountain ranges, the slow curve of the Earth. They were placed that far apart deliberately. A single detector, however sensitive, cannot distinguish a genuine gravitational wave from a passing truck, a distant tremor, a gust of wind finding its way into the structure. But 2 detectors, separated by a continent, sharing no local environment, if both register the same signal within the time it takes light to cross that distance, the odds of coincidence collapse. The separation is itself a form of certainty. Each detector is built in the shape of an L. 2 arms, meeting at a corner, each one precisely 4 kilometers long. 4 kilometers of steel tube, lying flat against the Earth, pointing outward in perpendicular directions. From above, they would look almost modest, 2 lines drawn across the landscape, meeting at a right angle, like the beginning of a map. Inside each arm, the tube has been emptied. Not merely pumped down to a low pressure, but evacuated to something close to the hardest vacuum humans have ever sustained over such a distance. The pressure inside is roughly 1/1,000,000th of normal atmospheric pressure. That is 1,000,000,000,000 times less air than the room you are lying in now. Less air, in fact, than exists in the space between planets. The tubes stretch 4 kilometers in each direction, and within them, almost nothing. This emptiness is necessary. Air molecules, even sparse ones, would scatter the laser light, introduce noise, blur the measurement. The beam must travel in silence, in stillness, in a vacuum that took years of engineering to achieve and requires constant maintenance to hold. At the far end of each arm, and at the corner where they meet, hang the mirrors. They are not ordinary mirrors. They are among the most perfectly polished objects ever made by human hands. Smooth to a degree that has no analogy in daily life. Surfaces so flat that if you scaled one up to the size of a continent, the tallest feature would be only a few centimeters high. They are made of fused silica, a form of glass of extraordinary purity, and their reflective coatings are applied with a precision measured in atoms. And they hang. Each mirror is suspended from the structure above it by glass fibers, threads of fused silica thinner than a human hair. This is not decoration. It is isolation. The Earth is never truly still. It breathes with the tides. It trembles with the footsteps of ocean waves breaking on shores thousands of kilometers away. Traffic on distant roads sends faint vibrations through the ground, through the foundations, upward into the structure. The glass fibers act as a mechanical filter, absorbing those vibrations before they can reach the mirror. The mirror is allowed to hang free, coupled to the Earth as loosely as physics permits. And even that is not enough. Beneath each mirror's suspension system lies a stack of active isolation platforms, mechanical stages that sense incoming vibrations and move in the opposite direction, canceling them in real time. These systems can suppress ground motion down to a fraction of a femtometer. A femtometer is 1/1,000,000th of a nanometer, a fraction of that. All of this, the vacuum, the mirrors, the fibers, the isolation, exists to protect a measurement. A laser beam enters the detector at the corner, where the two arms meet. It is split in two. One half travels down one arm, 4 kilometers to the far mirror, and reflects back. The other half travels down the other arm, 4 kilometers, and returns. The two beams are then recombined. If the arms are exactly equal in length, the beams cancel each other out when they meet, a phenomenon called destructive interference. The detector sees darkness. But if one arm has been stretched, even imperceptibly, and the other compressed, if the geometry of space itself has shifted, the beams no longer cancel perfectly. A faint pattern of light appears. That is the signal. The displacement LIGO is designed to detect is about 1/1000th the diameter of a proton. A proton is itself roughly 1/1,000,000th of a nanometer wide, 1/1000th of that. It is a number that resists intuition. It is smaller than anything that has a name in ordinary experience, and yet that is what LIGO was built to feel. The idea for this instrument did not arrive quickly. In the 1970s, 3 physicists began to think seriously about whether such a machine could be built. Rainer Weiss, working at MIT, had been developing the theoretical framework for laser interferometry as a gravitational wave detector. Kip Thorne, at Caltech, was one of the world's leading theorists of general relativity, deeply convinced that gravitational waves were real and detectable. Ronald Drever, also at Caltech, brought experimental ingenuity, a restless, inventive mind that pushed the technical boundaries of what precision measurement could achieve. They were not, at first, a smooth collaboration. The 3 men had different temperaments, different approaches, different visions for what the instrument should be. There were tensions, disagreements, long stretches of uncertainty about whether the project would survive at all. But the idea held. Through the 1970s and into the 1980s, the concept slowly gathered weight. Theoretical papers, prototype detectors, small-scale experiments testing whether the noise could be controlled, whether the mirrors could be made smooth enough, whether the vacuum could be held long enough. Each answer led to a harder question. Construction did not begin until 1994. 2 decades after the first serious conversations, ground was broken on 2 sites, one in the high desert of Washington State, one in the pine forests of Louisiana. The initial cost was roughly $365 million, making it, at the time, the largest investment the National Science Foundation had ever made in a single project. There were critics. There were scientists who believed the money could be better spent, that the sensitivity required was beyond reach, that the noise would never be tamed. The machine was built anyway. It ran. It listened. It heard nothing. Or rather, it heard too much. The Earth's own restlessness, the hum of civilization, the slow groan of tectonic plates. The noise floor was too high. The sensitivity was not yet enough. So it was rebuilt. Between 2010 and 2015, LIGO underwent a transformation. New mirrors, improved suspensions, more powerful lasers, better isolation systems. Advanced LIGO emerged with 10 times the sensitivity of its predecessor. 10 times. The volume of space it could now survey was not 10 times larger. It was 1,000 times larger, because sensitivity in distance translates to volume as a cube. And then it listened again. Quietly, in the high desert and in the pine forest, the two machines waited, arms outstretched, mirrors hanging in their near-perfect vacuum, isolation systems humming, laser light traveling back and forth in the dark. The universe had been sending its signals for billions of years. It had sent them through empty space, through galaxies, through the slow expansion of everything. And on a September morning in 2015, one of those signals, a ripple born from two black holes becoming one, 1.3 billion years before, arrived. Both machines felt it. Both machines felt it at almost the same moment, separated by a few thousandths of a second, just long enough for the ripple to cross the distance between Louisiana and Washington at the speed of light. The signal was real. For 5 months, the scientists said nothing publicly. They checked everything. They checked it again. They looked for earthquakes, for passing vehicles, for electromagnetic interference, for any conceivable explanation that did not involve two black holes merging 1 billion years ago. They found none. And on February 11th, 2016, they told the world. The announcement was made to a room full of scientists and journalists, and then broadcast outward to universities, to observatories, to anyone who was listening. The people in that room had spent careers preparing for this moment, or preparing for the possibility of this moment, not knowing if it would ever come. Some of them had been working toward it for 40 years. What they announced was this: a signal lasting less than 0.2 of a second, rising in frequency and amplitude before vanishing, a brief upward sweep, like a tone climbing quickly and then gone. Scientists called it a chirp, not metaphorically. That is the technical term. A chirp. Physicists took that signal and converted it into sound, shifted it into the range human ears can hear, and what emerged was something small and quiet, a soft thud, a brief, low murmur, rising slightly at the end, less than a second of sound. It has been called the first sound of the universe ever directly recorded. Not a recording of light, translated into sound, not a simulation, an actual oscillation in the fabric of space-time itself, converted into pressure waves in air, arriving in a human ear. The universe had been making this kind of sound, if sound is even the right word, for billions of years. Two black holes spiraling together somewhere in the dark, their merger sending a ripple outward in all directions. That ripple crossing 1.3 billion light years of expanding space, passing through everything without leaving a mark, and finally, briefly, moving two mirrors by less than 1,000th of a proton's width. And we heard it. To understand what that meant, it helps to remember what astronomy had been until that morning. Every telescope ever built, every mirror, every lens, every radio dish, every X-ray satellite had been listening to the same thing: light. Electromagnetic radiation in its many forms: visible light, radio waves, infrared, ultraviolet, X-ray, gamma ray, all of it the same, fundamental phenomena, just at different frequencies. For the entire history of human astronomy, that was the only signal available. The universe, as far as our instruments were concerned, existed only insofar as it glowed. But much of the universe does not glow, or glows in ways we cannot easily see. The interior of a black hole merger is forever hidden from light. The moments just after the Big Bang are opaque to electromagnetic radiation. Entire populations of objects, dark, cold, or simply too distant, have been invisible to every instrument we ever built. Gravitational waves pass through all of that. They are not blocked by dust, not scattered by gas, not absorbed by matter of any kind. They arrive carrying information about events that light could never describe. That morning in February 2016, a new sense opened. The collaboration that made it possible had grown far beyond its origins. What began as a small academic project in the 1970s, a handful of physicists with an idea and a great deal of uncertainty, had become something much larger. Barry Barish joined LIGO in the 1990s and transformed it. He brought the organizational structure of large-scale physics to what had been a relatively modest effort. Under his leadership, LIGO became a proper scientific collaboration, one capable of building, operating, and sustaining two enormous instruments across decades. It was Barish who made the scale possible, the scale that was necessary. By the time of the first detection, the LIGO scientific collaboration included over 300 scientists from more than 100 institutions around the world. Physicists, engineers, data analysts, theorists, people who had spent years writing software to search for signals and noise, people who had spent years perfecting mirror coatings, people who had spent years modeling what a black hole merger should look like in data. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish for LIGO, and for the detection of gravitational waves. 3 people named, representing thousands who contributed. The prize, as prizes do, compressed a vast collective effort into a small number of names, but the work itself had been genuinely shared across continents and decades. And the network was growing. LIGO had not been alone for long. Near Pisa, in the Italian countryside, a detector called Virgo had been operating and refining its own instruments. Its arms were 3 kilometers long, slightly shorter than LIGO's 4, but it worked on the same principles: laser light, split and recombined, sensitive to the faintest stretching of space. Virgo joined the Global Observation Network in 2017, and the collaboration between the two projects deepened. Having a second detector had always been essential for confirming a signal was real. Having a third changed something further. With 3 detectors spread across different parts of the Earth, scientists could begin to triangulate. A gravitational wave arrives at each detector at a slightly different moment, depending on the direction it came from. Those tiny time differences, fractions of milliseconds, encode the wave's origin in the sky. 3 detectors turn a detection into a location. Not a precise location, a region, an arc or patch of sky, sometimes large, sometimes smaller, but a direction, a place to point other telescopes. And then, in 2020, a 4th instrument joined the network, Kagra, built not on the surface, but inside a mountain in Japan, tunneled into the rock of the Kamioka mine, shielded from the seismic noise that reaches surface detectors. Underground, the Earth is quieter, the thermal noise is lower. Kagra represented a different approach to the same problem: how to hear something almost infinitely faint against a background that never fully falls silent. 4 detectors now, on 2 continents, and beneath a mountain, each one an extraordinary act of patience and precision, each one waiting, in its own stillness, for the universe to speak. The chirp from September 2015 had lasted less than a second, but what it carried had been traveling for 1.3 billion years. It had left its source before the first animals appeared on Earth. It had crossed the expanding space between galaxies, between galaxy clusters, through the large-scale structure of the cosmos. It had passed through the Milky Way without disturbing a single atom. It had passed through the Earth. It had passed through the detectors themselves, many times, before the detectors were sensitive enough to notice. And then, one morning, the universe does not wait for us to be ready. It sends its signals continuously, in all directions, without regard for whether anything is listening. For most of cosmic history, nothing was. The ripples move through emptiness, through matter, through time, unheard. What changed in 2015 was not the universe. What changed was us. We had built something still enough, precise enough, patient enough, We had learned to hold a mirror so steady that the passage of a wave smaller than a nucleus could move it measurably. We had learned to listen at a frequency the cosmos had been broadcasting since long before our sun existed. And in that listening, quiet, technical, painstaking, something shifted. Not loudly. The chirp itself was brief and soft, but the door it opened has no obvious closing. That door opened onto a universe we had never truly seen before. Not because the universe had changed, but because we were finally holding the right instrument. For all of human history, astronomy meant light. It meant gathering photons, visible light, radio waves, X-rays, infrared, and reading what they carried. Every telescope ever built, every observatory ever placed on a mountaintop or launched into orbit was a collector of electromagnetic radiation in one form or another. And that light told us an enormous amount. It revealed the composition of stars, the rotation of galaxies, the expansion of space itself. But light has limits. There are places in the universe that light cannot leave. A black hole, by definition, is a region from which no electromagnetic signal escapes. The event horizon is a one-way boundary. Matter and light fall inward, and nothing returns. Whatever happens at the moment, two black holes finally meet. Whatever violence and geometry unfolds in those final fractions of a second, it is permanently sealed from any light-based instrument. Gravitational waves are not sealed. They pass through the event horizon as freely as they pass through anything else. They carry the full record of the merger outward into space, the mass, the spin, the final ring down, encoded in the shape of the wave itself. For the first time, we had a way to read a message from inside the darkness. That was already something extraordinary. And then, on the 17th of August, 2017, the universe offered something more. At 12:41 in the afternoon, Coordinated Universal Time, LIGO and its European partner Virgo detected a gravitational wave signal unlike any they had recorded before. It was longer, slower, more intricate than the brief chirps of merging black holes. It built gradually over nearly 100 seconds, two objects spiraling closer and closer, their gravitational waves rising in pitch and intensity as the distance between them shrank. The objects were not black holes. They were neutron stars. Neutron stars are what remain when a massive star exhausts its fuel and collapses. Not massive enough to become a black hole, but far too dense to remain anything ordinary. The collapse compresses the core to a sphere roughly 20 kilometers across, about the width of a city, while packing in more mass than the entire sun. A single teaspoon of that material, brought somehow to Earth, would weigh roughly 4 billion tons. They're among the most extreme objects the universe produces, and two of them, in a galaxy called NGC 4993, about 130 million light-years away in the constellation Hydra, had been orbiting each other for a very long time, slowly, patiently, losing energy to gravitational waves with every orbit, drawing closer across millions of years, until that August morning, when the last of the distance between them finally closed. The gravitational wave signal reached the detectors first. And then, 1.7 seconds later, an almost impossibly brief interval on cosmic timescales, orbiting telescopes detected a burst of gamma rays. 1.7 seconds? That gap is itself a measurement. It tells us that gravitational waves and light travel at speeds so nearly identical that any difference across 130 million light-years of travel amounted to less than 2 seconds. The speed of gravitational waves confirmed to match the speed of light to within 1 part in 1,000 trillion. But the gamma ray burst carried its own significance. For decades, astronomers had observed short gamma ray bursts, intense flashes of the highest energy light in the universe, lasting only a second or two, and had suspected, without being certain, that they came from neutron star mergers. The geometry was right, the energetics were plausible, but no one had ever caught one in the act. GW 170817 caught one in the act. The theory was confirmed, quietly and completely, by a signal that had been traveling since before the first fish appeared in Earth's oceans. And the event was not finished. In the hours and days that followed, something else emerged at the location of the merger. A glowing, expanding cloud, visible across many wavelengths of light, that astronomers call a kilonova. It was the afterglow of creation, not the destruction of matter, but its transformation. When two neutron stars collide, the conditions briefly achieved are unlike anything that exists elsewhere in the present universe. Temperatures and pressures so extreme that atomic nuclei are built up rapidly, capturing neutrons faster than they can decay. This process, the rapid neutron capture process, the R process, forges elements that cannot be made inside ordinary stars. Heavy elements, dense elements, elements that require more neutrons packed into a nucleus than stellar fusion can provide. Gold is one of them. Platinum is another, and iridium and osmium and many others that sit in the lower reaches of the periodic table. The kilonova from GW 170817 produced, as best as scientists can estimate, a mass of gold equivalent to several times the mass of the Earth. Not metaphorically, literally, several Earth masses of gold, freshly forged in the collision of two dead stars, expanding outward into space at a fraction of the speed of light. The gold in a ring, in a coin, in any object made of that metal. It did not form in the sun, or in any star like the sun. It formed, most likely, in a collision like this one. In the final moments of two neutron stars that had been circling each other for longer than the Earth has existed. That is where it came from. That is where most of the heavy elements came from. And we know this now, with a confidence we did not have before August 17, 2017, because of a gravitational wave signal and the light that followed it. More than 70 observatories around the world turned toward NGC 4993 in the hours and days after the detection. Radio telescopes, optical telescopes, X-ray satellites, ultraviolet instruments, infrared arrays. Every available eye pointed at the same small patch of sky, watching the kilonova brighten and then slowly fade. Each wavelength revealing a different layer of the event, a different chapter of the same story. This was something new in the history of science. Not just a new detection, but a new method. Multi-messenger astronomy, the practice of studying a single cosmic event through multiple, independent signals simultaneously. Gravitational waves carrying the geometry of the merger. Gamma rays carrying the energy of the collision. Optical light carrying the chemistry of the newly formed elements, each messenger confirming and extending what the others reveal. The universe had been sending all of these signals together, from the same event, for 130 million years. We received them within seconds of each other. And in receiving them together, we understood something we could not have understood from any one of them alone. There is a quietness to all of this when you sit with it long enough. Two small, dense objects, each one the compressed remnant of a star that once burned for millions of years, finding each other across the void, orbiting for an unimaginable span of time, and finally merging in a fraction of a second. Forging gold in the process, sending ripples through the fabric of space, sending light across 130 million light years, and arriving, at last, at a network of instruments built by a few thousand people on a small planet. Instruments sensitive enough to feel the passage of a wave smaller than a nucleus. Patient enough to wait for the signal. Still enough to hear it. That stillness is worth staying with a little longer. Because what merged that day was not just two objects. It was two of the strangest things the universe has ever made. Neutron stars. The word alone does not prepare you for what they are. When a massive star exhausts its fuel after millions of years of burning, its core collapses in less than a second. The outer layers explode outward in a supernova, and what remains at the center is compressed beyond almost any limit we can describe. A sphere roughly 20 kilometers across, smaller than many cities on Earth. And yet, more massive than the sun. All of that mass, pressed into a space that's small, creates conditions that exist nowhere else in the observable universe. The atoms themselves cannot survive it. Electrons are forced into protons. The entire object becomes, in a sense, a single enormous atomic nucleus, dense beyond ordinary reckoning. A single teaspoon of neutron star material, just that small volume, would weigh roughly 4 billion tons here on Earth. 4 billion tons. In a teaspoon, there is no comfortable way to hold that number. It simply sits there, patient and true, asking nothing of you. And these objects spin. As a star collapses, it conserves its rotation the way a skater pulling in their arms begins to turn faster. A star that rotated slowly over millions of years becomes, in its collapsed form, something that can spin hundreds of times every second. Hundreds of full rotations per second. Some neutron stars emit narrow beams of radio waves from their magnetic poles. As they spin, those beams sweep across space like the beam of a lighthouse. If the Earth happens to lie in the path of that beam, we receive a pulse with each rotation, regular, precise, almost metronomic. These are pulsars, and their regularity is extraordinary. Some of them keep time more accurately than the finest clocks we have built. Now hold that image gently. Two of these objects, orbiting each other. They circle one another through the void, bound by gravity, each one a compressed remnant of a star that once burned for millions of years. And as they orbit, they do something that Einstein's equations quietly predicted. They radiate gravitational waves. Not in a single burst, but continuously, steadily, with every orbit. The waves carry energy away from the system, and as energy leaves, the orbit shrinks, slowly, almost imperceptibly. The two stars draw a little closer with each pass. This process takes a very long time, millions of years, sometimes billions. But it is relentless. In 1974, two astronomers made a discovery that would carry this idea from theory into something measurable. Russell Hulse and Joseph Taylor were using a radio telescope in Puerto Rico when they found something unusual. A pulsar, but not alone. It was orbiting another neutron star, a binary pulsar, the first one ever found. They called it the Hulse-Taylor binary pulsar. And because one of the two stars was a pulsar, ticking with that extraordinary regularity, they had, in effect, a clock embedded in the system. A clock precise enough to measure the orbital period to many decimal places. They watched it for years. And the orbital period was changing. The two stars were slowly spiraling inward, exactly as Einstein's equations predicted they should if gravitational waves were carrying energy away. The match between observation and prediction was almost unsettling in its precision. Within 0.2%, not roughly correct, not approximately right, within 0.2%. For this, Hulse and Taylor received the Nobel Prize in Physics in 1993. And for the scientific community, this was enough. Not a direct detection, the waves themselves had not been felt, but the evidence was so clean, so precise, that confidence in gravitational waves held firm for the next 4 decades. 4 decades of building, of waiting, of refining instruments toward a sensitivity that had never existed before. All of it resting, in part, on the quiet orbital decay of 2 neutron stars circling each other in the dark. And then there are black holes. If neutron stars press matter to its limits, black holes pass beyond them entirely. A black hole forms when a massive star, far more massive than those that leave neutron stars behind, exhausts its fuel and collapses. The collapse does not stop. There is nothing left to stop it. The matter falls inward past any density we have equations to describe. And what remains is a region of space-time where gravity has become absolute. So strong that nothing escapes. Not particles, not radiation, not light itself. There is a boundary around this region, a surface of no return, called the event horizon. From outside the event horizon, you can feel the black hole's gravity. You can orbit it as stars and gas clouds do. You can even, in principle, fall toward it. But once you cross that boundary, the geometry of space-time itself has changed in a way that makes return impossible. Every path forward leads inward. There is no direction that leads out. The event horizon is not a physical surface. It is a feature of the geometry, a threshold written into the shape of space-time. And black holes, like neutron stars, can find each other. Two black holes in a binary system, perhaps the remnants of two massive stars that once burned together, orbit one another across an enormous distance. And they too radiate gravitational waves with every orbit. They too spiral slowly inward. But the timescales are vast. Millions of years, sometimes billions, of slow, patient inward drift. As the distance between them decreases, the gravitational waves they emit grow stronger, the orbit tightens, the frequency of the waves rises, the in-spiral accelerates. And then comes the final approach. The last fraction of a second before the two black holes touch is called the plunge. In that moment, the gravitational wave energy being released surpasses anything else in the observable universe. More energy, radiated in that instant, than all the stars in the cosmos emit in light during that same sliver of time. And then they merge. The two event horizons meet and become one. But it is not immediately still. The newly formed black hole is not yet settled. It is distorted, asymmetric, vibrating with the memory of the collision, and it does what any struck object does. It rings. Like a bell that has been struck, the black hole oscillates, emitting gravitational waves as it does, each oscillation slightly smaller than the last. The waves fading as the black hole settles toward its final, symmetric shape. This is called the ring down. And the frequency of that ringing, the precise tone of it, encodes the mass and spin of the new black hole, a signature written in the geometry of spacetime itself. Physicists can read that signature. They can compare it against what general relativity predicts a black hole of that mass and spin should sound like. And so far, every time, the match has been exact. That match has held across every event recorded so far. And it is worth pausing on what that means. General relativity is now more than a century old. It was written down by a single person, working largely alone, guided not by experiment, but by the deep conviction that the universe must be elegant. And yet, it has survived every test that modern science has been able to devise. From the bending of starlight around the sun, to the slow drift of Mercury's orbit, to the ticking of atomic clocks aboard satellites, to the ring down of black holes more than 1 billion light years away. Every time, the numbers match. There is something almost unsettling about that. A theory so precise, so far-reaching, that even its most extreme predictions, black holes, gravitational waves, the ringing of space-time itself, turn out to be exactly right. The ring down carries more than just mass and spin. Gravitational waves also transport angular momentum, the quality of rotation, of spin. As the waves carry energy away from the merging system, they also carry away some of its rotational motion. This shapes the final black hole. Its spin, its orientation, the way it settles. All of it is influenced by what the waves have taken with them. The wave and the object are not separate things. They are part of the same process. The black hole sheds its asymmetry through the waves, and the waves carry that asymmetry outward into the universe. It is a kind of conversation between geometry and motion, written in a language that took us a century to learn to read. There is one event that tested general relativity in a different way. Not through ring down, but through speed. On the 17th of August, 2017, LIGO and Virgo detected gravitational waves from two merging neutron stars. The signal was different from the black hole mergers, longer, more delicate, rising slowly over nearly 2 minutes as the stars spiraled closer. And then, roughly 2 seconds after the gravitational wave signal arrived at Earth, orbiting telescopes detected a burst of gamma rays from the same direction in the sky. 2 seconds. After traveling 130 million light years, the gravitational waves and the light arrived almost simultaneously. That gap of 2 seconds, across that vast distance, placed an extraordinary constraint on the speed of gravitational waves. They travel at the speed of light, not approximately, not roughly, but to within 1 part in 1,000 trillion. That number is almost too precise to hold in the mind. 1 part in 1,000 trillion. It means that if you sent a gravitational wave and a beam of light on a journey of 130 million light years, they would arrive within 2 seconds of each other. This was not merely a confirmation of what everyone expected. For decades, physicists had proposed alternative theories of gravity, modifications to general relativity that might explain certain puzzles in cosmology. Many of these theories made subtly different predictions about how gravitational waves would propagate. Some predicted the waves would travel slightly slower than light. Others, slightly faster. The differences were small, but they were there. In a single observation, GW 1708-17 ruled out hundreds of these theories. Not weakened them, not cast doubt on them, ruled them out. The universe had spoken with unusual clarity, and most of the alternatives simply could not survive what it said. What remained standing, once again, was Einstein's original framework, unchanged, unmodified, holding its shape against everything we could throw at it. There is something else worth understanding about how gravitational waves move through space. They are transverse waves. This means they do not push and pull in the direction they are traveling. They stretch and squeeze space in the directions perpendicular to their motion. Sideways, in a sense, though that word is imprecise when we are talking about the fabric of space-time itself. Picture a wave moving toward you. It does not compress the space between you and its source. Instead, it gently stretches the space to your left and right, and simultaneously compresses the space above and below. Then it reverses. What was stretched becomes compressed. What was compressed becomes stretched. All of this happening in a fraction of a second, at the scale of 1,000th of a proton's width. This is called the plus polarization, named for the shape it traces in space, a cross aligned with the horizontal and vertical. But gravitational waves have a second polarization as well. The cross polarization does the same thing, the same stretching, the same squeezing, the same reversal, but rotated 45 degrees. So instead of stretching left-right and compressing up-down, it stretches along the diagonals. These two polarizations are not separate waves. They are two aspects of the same wave, two ways the same ripple can orient itself as it moves through space. LIGO's shape was not chosen by accident. The two arms, arranged in an L, at right angles to each other, are sensitive to both polarizations at once. When a gravitational wave passes, one arm stretches while the other compresses, and the precise pattern of that stretching and compressing carries information about which polarization, or which combination of polarizations, the wave carries. Detecting both polarizations from a single event is not just a technical detail. It helps confirm the fundamental nature of the wave. It tells physicists how the source was oriented in space, which direction the merging objects were spinning relative to Earth, how the system was tilted as it radiated. A single polarization would tell part of the story. Both polarizations together tell something closer to the whole. And so the wave arrives at the detector carrying all of this within it. The mass of what merged, the spin of what remained, the speed at which the wave traveled, the orientation of the system that produced it, the polarization state of space-time as it passed. All of it encoded in a displacement smaller than any human instrument had ever been asked to measure. All of it extracted, carefully, patiently, by scientists who had spent decades building something quiet enough to listen. There is a kind of patience in this work that is difficult to describe. The theory was written in 1916. The first detector concepts came in the 1970s. Construction began in the 1990s. The first detection came in 2015. Nearly a century from prediction to confirmation. And the wave itself had been traveling for far longer than that. It left its source 1.3 billion years ago, when the most complex life on Earth was still single-celled, when there were no eyes to see, no ears to hear, no minds to wonder. It crossed that distance in silence, passing through galaxies, through clouds of gas and dust, through the expanding space between everything, and arrived, at last, at two quiet machines in the American landscape, where it stretched and squeezed the arms of an interferometer by a distance that has no everyday analogy, and was heard. And yet, the story does not end there. What was heard in 2015 was old, ancient, even. But there are older signals still, signals that may have been traveling since before the universe had any structure at all. In the first fractions of a second after the Big Bang, the universe underwent something called inflation, a period of extraordinarily rapid expansion. Space itself stretched faster than light can travel, growing from something unimaginably small to something vast, in a sliver of time too brief to name. If that expansion was real, and most cosmologists believe it was, then it would have generated gravitational waves, primordial gravitational waves, ripples pressed into the fabric of space-time at the very moment the universe began to take shape. Those waves, if they exist, may still be moving through space today. They would be ancient beyond any ordinary sense of the word, not a billion years old, not several billion, but as old as time itself, very nearly older than the first atom, older than the first photon of light, older than anything we have ever observed. We have not detected them yet, but we are looking. The afterglow of the Big Bang, a faint wash of microwave radiation that fills the entire sky, may carry their imprint. This afterglow is called the cosmic microwave background. It is light that has been traveling since the universe was roughly 380,000 years old. Ancient light, cooled now to just a few degrees above absolute zero, spread evenly across the heavens like the last warmth of a fire that burned almost 14 billion years ago. Primordial gravitational waves would have left a subtle pattern in that light, a faint twist in its polarization, a gentle spiraling in the way the light's electric field is oriented as it arrives at our instruments. Experiments built in some of the coldest, driest places on Earth are searching for exactly that pattern. Telescopes like BICEP and the Keck Array, stationed near the South Pole where the atmosphere is thin and still, scan the microwave sky with extraordinary care, looking for the faint curl that would mean inflation happened, that the universe's first moments left a mark we can still read. It is a delicate search. The signal, if it is there, is buried beneath other sources of polarization, dust in our own galaxy, the accumulated glow of distant stars. Separating the primordial from the local requires patience of a particular kind. So far, no confirmed detection. But the search continues, quietly, at the bottom of the world. And in space, a new instrument is being prepared. In the 2030s, the European Space Agency plans to launch something called LISA, the Laser Interferometer Space Antenna. It will be, in a sense, LIGO's larger, slower sibling, but the scale is almost impossible to hold in the mind. LISA will consist of 3 spacecraft, flying in a triangular formation, separated from one another by 2.5 million kilometers. Each side of that triangle is a gravitational wave detector arm, each one 2.5 million kilometers long. For comparison, LIGO's arms are 4 kilometers. LISA's will be 600,000 times longer. The 3 spacecraft will follow the Earth in its orbit around the Sun, trailing behind like a quiet constellation of their own, exchanging laser beams across the void between them, measuring, with extraordinary precision, any change in the distances between them. A gravitational wave passing through that triangle would shift those distances, and Lisa would feel it. But Lisa will not be listening for the same sounds LIGO hears. It will be tuned to a different register entirely, lower frequencies, slower oscillations, the deep, slow movements of very large, very massive systems. LIGO hears the final moments of stellar mass black holes, objects tens of times the mass of the Sun, spiraling together in fractions of a second. Their gravitational waves are brief and high-pitched by cosmic standards. Lisa will hear something else. At the center of nearly every large galaxy in the universe, there is a black hole of a different order entirely. Supermassive black holes, millions of times the mass of the Sun, some billions of times, sitting at the hearts of galaxies like vast, dark anchors. Our own galaxy has one, Sagittarius A star, roughly 4 million solar masses, quiet now, for the most part, but present. When two galaxies collide, and galaxies do collide, slowly, over hundreds of millions of years, their central black holes do not immediately merge. They sink toward each other through the combined gravity of the new, merged galaxy, circling, drawing closer, over timescales that dwarf anything in human experience. Eventually, they spiral together. And when they do, the gravitational waves they release would be among the most energetic events the universe has ever produced. Waves so powerful, so low in frequency that no ground-based detector could ever sense them. The Earth itself is too small, too noisy, too rigid in the wrong ways. But Lisa, floating free in space, will be able to hear them. It will open a new band of the gravitational wave spectrum, the way a new kind of telescope opens a new band of light. And in that band, an entirely different population of events will become visible. Compact binary systems that have been slowly spiraling for millions of years. The distant rumble of supermassive mergers from across the observable universe, perhaps even signals from the early cosmos itself. And there's another instrument already listening, one that was not built for this purpose, but has become one of the most remarkable detectors ever conceived. Scattered across the galaxy, there are pulsars, neutron stars spinning hundreds of times per second, emitting beams of radio waves with the regularity of the finest clock ever made. Each pulse arrives at Earth on a schedule so precise that deviations of a few hundred nanoseconds can be measured and studied. A network of these pulsars, observed simultaneously over years and decades, becomes something extraordinary, a gravitational wave detector the size of the galaxy itself. When a gravitational wave passes through the Milky Way, it stretches and squeezes the distances between us and these pulsars, very slightly, very slowly. The pulses arrive a little early, or a little late, in a pattern that reflects the wave passing through. This is called a pulsar timing array. And in 2023, several independent collaborations around the world, teams in North America, Europe, India, China, and Australia, each reported evidence for something they had been searching for quietly for years: a gravitational wave background, a low, constant hum of overlapping waves from countless merging black holes spread across cosmic history. Not a single event, not one chirp from one collision, but the accumulated signal of an entire universe's worth of mergers, blending together into something like ambient sound. The universe's own background noise. A deep, slow rumble that has been present all along, beneath everything, unheard, until now. And that hum is still there now. As you lie here, it is passing through you. Slowly, silently, a trembling in the fabric of space itself, too low and too vast for any instrument yet built to fully resolve, but present, woven into the background of everything. The teams who found it did not announce it with certainty. They spoke carefully, as scientists do when the universe offers something genuinely new. They said, evidence. They said, consistent with. They said, we believe this is real, and we are still learning what it means. What it means As far as we can tell, is this across the entire history of the cosmos. Black holes have been finding each other, circling, drawing closer, merging, and each merger has sent ripples outward into space. For billions of years, those ripples have been accumulating, overlapping, blending, until they form something less like a single voice and more like a chorus, a vast, unresolved chord that fills the universe from edge to edge. That is what the pulsar timing arrays found. Not one event, not one collision, but the sum of all of them. Every merger that ever happened, across every galaxy, across every age of the universe, arriving together as a kind of cosmic undertone. It has always been there. Now, quietly, scientists are thinking about what comes next. The detectors that exist today, LIGO, Virgo, Cagra, are extraordinary instruments. They have already changed what we know, but they are also, in a sense, just the beginning. There are proposals on the table for something larger, something more still. One is called the Einstein telescope, a European concept, still in the planning stages. It would be built underground, deep beneath the surface of the Earth, shielded from the constant small tremors that move through the ground above, the footsteps of traffic, the slow breathing of tides, the distant shudder of storms at sea. Underground, those disturbances fade. The rock itself becomes a kind of quiet. The Einstein telescope would be triangular in shape, 3 arms arranged in a triangle rather than an L. This geometry would allow it to measure both polarizations of a gravitational wave simultaneously, with greater precision than any detector before it. And its sensitivity would reach into frequency ranges that current instruments can only glimpse at the edges. On the other side of the Atlantic, a different proposal takes shape. Cosmic Explorer, an American concept, with arms 40 kilometers long. 40 kilometers. LIGO's arms are 4 kilometers, and that alone required some of the most precise engineering ever attempted. Cosmic Explorer would be 10 times that length, each arm stretching across the landscape like a quiet road going nowhere, sealed inside a vacuum, waiting. With arms that long, the displacement caused by a passing gravitational wave would be proportionally larger, still unimaginably small by any ordinary measure, but large enough for instruments to read with a clarity that current detectors cannot achieve. Together, instruments like these could reach the very edge of the observable universe. They could detect gravitational waves from events so distant that the light from those same events has not yet reached us and may never reach us. The universe is expanding, and some of its oldest light is being carried away faster than it can arrive. But gravitational waves, traveling at the same speed as light, would carry the same limitation. And yet, with enough sensitivity, the signals from the earliest mergers might still be within reach. What scientists hope to find there is something almost too large to hold in mind. The first stars. The universe's first generation of stars formed from hydrogen and helium alone. In the darkness before any heavier elements existed, they were enormous, far more massive than most stars that form today, and they burned fast and died young, and some of them collapsed into black holes. The first black holes the universe ever made. If 2 of those ancient black holes found each other and merged, the gravitational waves from that merger are still traveling. They have been traveling for nearly 14 billion years. And if our instruments become sensitive enough, we might one day receive them. That signal would be a message from before the Earth existed, before the sun existed, before any of the atoms in your body had been forged. For now, the catalog of what we have already found continues to grow. Every gravitational wave event receives a name, simple and systematic. GW, for gravitational wave, followed by the date of detection. GW 150914 for the 14th of September, 2015. GW 170817 for the 17th of August, 2017. Each name is a coordinate in time, a marker placed quietly in the record. By the end of LIGO's 3rd observing run, more than 90 events have been confirmed. 90 ripples in space-time, each one cataloged, each one studied. The catalog holds binary black hole mergers, two black holes spiraling together and becoming one. It holds neutron star mergers, like GW 170817, where the collision forged gold and sent light across the sky. And it holds something rarer still, events that appear to be mixed pairs, one black hole and one neutron star, orbiting each other, drawing closer, until the neutron star crosses the threshold and is consumed. The first confirmed detection of a mixed pair came in 2021. What happens in that moment, when a neutron star falls into a black hole, depends on the sizes involved. If the black hole is large enough, the neutron star may pass the event horizon largely intact, swallowed whole before tidal forces can tear it apart. If the black hole is smaller, the neutron star may be shredded first, its matter stretched into a thin stream spiraling inward. The gravitational wave signal carries the imprint of which fate occurred. Each event in the catalog is a data point, a single measurement added to a growing picture. And the picture, as it fills in, has begun to show things that were not expected. The black holes detected by LIGO do not all fit neatly into the populations that stellar models predicted. Some are more massive than theory suggested was easily possible. Some fall in ranges that were once thought nearly empty. The distribution of masses, spins, and merger rates is telling a story about how stars live and die across cosmic time, a story that is still being read carefully, one event at a time. There is no rush. The universe has been sending these signals for billions of years. It will continue sending them long after every instrument we have built has fallen silent. The mergers happening tonight, in galaxies too distant to name, are already producing ripples that will reach this small planet millions or billions of years from now. And perhaps, by then, something will be listening. For now, the detectors stand in their quiet fields and their underground chambers, the mirrors hanging on threads of glass, the lasers tracing their paths back and forth in the dark, waiting for the next tremor in the fabric of space to pass through. And it will. It always does. There is a range of masses that sits like a gap in the landscape of what stars can become. Between roughly 50 and 130 times the mass of the Sun, theory long suggested there should be very few black holes. The reason is subtle and quiet and strange. When a star grows massive enough, the core of its final collapse becomes so hot that the gamma rays inside begin spontaneously creating pairs of electrons and their antimatter counterparts. This drains pressure from the core. The star becomes unstable, and instead of collapsing cleanly into a black hole, it tears itself apart in a catastrophic explosion, leaving little or nothing behind. This is called the pair instability gap. For a long time, it was thought to be nearly empty, a forbidden zone in the architecture of stellar death. And then the detectors began to listen. Some of the black holes found in LIGO's catalog sit squarely inside that gap. Their masses are too large to have come from a single collapsing star, at least by the pathways theory had mapped out. They are there, and they are real, and their presence asks a question that stellar physics is still working to answer. One possibility is quiet and almost elegant in its simplicity. In the densest regions of the universe, the cores of ancient globular clusters, where stars are packed so closely that the sky would blaze with light, black holes do not simply orbit and merge once. They can merge and then merge again. A black hole formed from a stellar collapse acquires a companion. They spiral together and become one. That new, larger black hole drifts through the cluster and in time finds another partner. The process repeats. Mass accumulates through successive collisions, each merger building on the last. These are called hierarchical mergers, and they offer a path into the gap that single stars cannot take. The cluster becomes, in a sense, a slow forge, not the sudden fire of a supernova, but a patient accumulation across millions of years, collision by collision, each one sending its own brief ripple outward through the fabric of space. The gravitational wave signal carries more than just the masses of the objects involved. It carries, encoded in its shape, something about how those objects were spinning and how their spins were oriented relative to each other. This matters more than it might seem. When two black holes form together from a binary star system, two stars born near each other, living their lives in each other's gravity, dying in sequence, their spins tend to point in roughly the same direction. They have shared a history. The angular momentum of the original system is written into them both. But when two black holes find each other by chance, drifting through a dense cluster, drawn together by the accumulated gravity of thousands of neighbors, there is no shared history to align them. Their spins point in whatever directions they happen to have when they met. Tilted, misaligned, sometimes nearly opposite. The gravitational wave signal from such a pair carries the signature of that randomness. A slight wobble in the waveform, a precession, a slow rotation of the orbital plane as the two objects spiral inward. These features are subtle, and extracting them requires careful analysis, but they are there. And so, across the growing catalog of events, physicists are beginning to read a kind of census. How many black holes formed in quiet binary systems, their spins aligned like compass needles pointing the same way? How many were assembled by chance in the crowded hearts of clusters, their spins scattered at random angles? The ratio between these populations tells a story about where black holes come from and how the universe distributes them across its vast and varied structures. It is a slow kind of cartography, mapping not places, but histories, not where things are, but how they came to be. And the neutron stars carry their own kind of information. When two neutron stars spiral toward each other in the final moments before merger, something happens that has no equivalent anywhere in a laboratory on Earth. Each star begins to feel the gravity of the other, not just as a pull toward a point, but as a tide. The near side is pulled more strongly than the far side. The star stretches, very slightly, along the line connecting them. It deforms. How much it deforms depends on what it is made of. This is the equation of state, a description of how matter behaves under pressures so extreme that the very identity of its constituents becomes uncertain. Whether the neutrons inside remain as neutrons or dissolve into something stranger, quarks moving freely, or exotic phases of matter that have no name in ordinary physics. No particle accelerator can reach these pressures. No experiment on Earth can compress matter to the density found at the center of a neutron star. The interior of a neutron star is, in a real sense, inaccessible to direct study, except through the waves. The tidal deformability of a neutron star, the degree to which it yields and stretches in its companion's gravity, leaves a faint but readable imprint on the gravitational wave signal. A stiffer equation of state, where matter resists compression more strongly, produces a star that deforms less and radiates slightly differently in the final moments before contact. A softer equation of state produces a more pliable star, one that stretches more readily, leaving a different mark on the wave. The difference is small. It requires careful measurement and careful analysis to extract, but it is there, written into the shape of the signal the way the grain of wood is written into the sound of a struck instrument. From GW 170817, the neutron star merger detected in 2017, physicists were able to place constraints on this deformability. The measurements suggested that neutron stars are relatively compact, radii somewhere around 11 to 13 kilometers, and that the matter inside them, while extraordinarily dense, is not infinitely stiff. It was a measurement of nuclear physics made not in a laboratory, but across 130 million light-years of space. The neutron stars themselves were the experiment. Their merger was the instrument, and the gravitational wave was the result, arriving after its long journey to be read by mirrors hanging in the quiet dark. There is something worth resting with, here, in the stillness before sleep. The universe contains matter in states we cannot reproduce, pressures we cannot generate, densities we cannot approach. And yet the information about those states does not stay locked away inside the objects that contain them. It travels outward. It is encoded in the shape of the disturbance those objects make in the fabric of space as they fall toward each other, and it crosses whatever distance lies between them and us. And it arrives, after however many millions or billions of years, as a tremor smaller than any tremor that has a name. And we have learned to read it. Not perfectly, not completely. The equations of state are still being narrowed. The populations of black holes are still being mapped. The pair instability gap still holds questions that have not yet been answered. But the reading has begun, and each new event adds another sentence to a text that the universe has been composing since long before the Earth existed. That tidal measurement, the way the two neutron stars stretched and deformed in each other's gravity before they finally met, told us something about their size, something that no telescope could have revealed on its own. The best current reading from GW 170817 suggests neutron stars are relatively compact, radii somewhere around 11 to 13 kilometers. A city, the collapsed core of a star that once burned for millions of years, compressed into something the size of a city. And the shape of the wave carried that information across 130 million light years. There is a quietness to that fact that is worth staying with for a moment. The same event, that single collision in the constellation Hydra, offered something else as well. Something that touches not just the nature of matter, but the nature of the universe itself. Astronomers have long wanted to know how fast the universe is expanding. The rate has a name, the Hubble constant, and it describes how quickly the fabric of space is stretching between galaxies. For decades, two different methods of measuring it have returned two different answers. Not wildly different, but different enough to be troubling. Different enough that at least one of them, or perhaps both, must be missing something. One method looks at the early universe, at the faint glow left over from the Big Bang, the cosmic microwave background, and extrapolates forward. The other method looks at the nearby universe, using the brightness of certain stars and supernovae to measure distances and recession speeds. Both methods are careful. Both have been refined over many years, and yet they disagree. This disagreement has a name too: the Hubble tension, a quiet word for a problem that has unsettled cosmology for years. Gravitational waves offer a third path. When a gravitational wave event occurs, the shape of the signal encodes the distance to the source directly, not through a chain of assumptions about stellar brightness or cosmic history, but through the physics of the wave itself. The amplitude of the wave, how loud it is, in a sense, falls off with distance in a predictable way. And so the distance can be read from the signal alone. Pair that distance with the recession speed of the host galaxy, how fast it is moving away from us as the universe expands, and you have an independent measurement of the Hubble constant. No rungs on a distance ladder, no calibration against other objects. The wave, in a sense, self-calibrating. This idea has a name, a standard siren, coined by analogy with the standard candles of light-based astronomy, objects whose intrinsic brightness is known, and which can therefore be used as distance markers. A standard siren does the same thing, but with sound rather than light, with gravity rather than brightness. The term was proposed by a physicist named Bernard Schutz in 1986, nearly 3 decades before the first gravitational wave was detected. He saw the possibility before the instrument existed to realize it, before LIGO had been built, before the first interferometer arm had been laid into the Louisiana soil. He simply worked through the mathematics and understood what the waves would carry, if they could ever be heard. GW 170817 was the first event to use this method in practice, because the host galaxy, NGC 4993, was identified, its recession speed was known, and the gravitational wave signal gave the distance. The result was a value for the Hubble constant that sat, as it happens, between the two competing measurements from other methods. Not resolving the tension, but entering the conversation. As more events accumulate, and they are accumulating, slowly, event by event, the gravitational wave measurement will grow more precise. The uncertainty will narrow. And at some point, it may become clear whether the tension is a systematic error in one of the older methods, or something deeper, something that requires new physics to explain. That question remains open, resting in the data, patient as the universe itself. And the universe has been patient for a very long time. Long before any star ignited, long before any galaxy had assembled itself from the slow gathering of gas and dust, the universe was already producing gravitational waves. In its earliest moments, fractions of a second after the beginning, the cosmos passed through a series of transitions. Moments when the fundamental forces and fields that govern matter changed their character, settled into new configurations. The way water changes when it freezes, or when it boils, but at energies and temperatures so extreme that no analogy quite reaches them. These transitions may not have been smooth. If they were turbulent enough, if the cosmos churned and buckled as it changed state, they would have sent gravitational waves outward into the expanding fabric of space, waves that have been traveling ever since, stretched by the expansion of the universe into frequencies so low that no ground-based detector could ever hear them. One such transition, the electroweak phase transition, when the electromagnetic force and the weak nuclear force separated into their distinct identities, may have been violent enough to leave a detectable signature. LISA, the space-based observatory planned for the 2030s, with its arms 2.5 million kilometers long, may be sensitive to exactly this frequency range. It may, if the physics is right, hear an echo of that moment. An echo from before the first star, before the first atom had fully cooled into being. There are also, in some theories, structures called cosmic strings, hypothetical defects in the fabric of space-time itself, one-dimensional threads, thinner than any particle, stretching across cosmic distances, relics of earlier phase transitions, where the geometry of space did not quite knit back together smoothly. If they exist, they would oscillate, and oscillating distortions of space-time produce gravitational waves. The strings would hum, in a sense, as they moved, sending ripples outward across whatever distances separated them from everything else. No cosmic string has been confirmed. They remain hypothetical, but gravitational wave observations are already placing limits on how common they could be and how much energy they could carry. Each new observing run tightens those limits a little further. The absence of a signal is itself a kind of signal. It tells us something about what the early universe did not contain, or did not do. And so the search continues in both directions at once, backward toward the earliest moments, and outward toward the faintest and most distant events still occurring today. The universe has been composing this record since before it had any structure worth naming, since before the forces that govern matter had settled into their present forms, since before the first proton had assembled itself from the quarks that preceded it. All of that history is, in principle, encoded somewhere in the gravitational wave background, in the low, slow hum that underlies everything, the sum of every collision, every transition, every oscillating defect across all of cosmic time. We are only beginning to learn how to read it. The instruments grow more sensitive with each generation. The catalogs grow longer. The questions grow more precise, even as some of them grow deeper. And somewhere in the data that has already been collected, in the archives that are open to any scientist who wishes to look, there may be answers waiting that no one has yet found the right question to ask for. The universe does not withhold. It simply continues, encoding everything in the geometry of the space it fills, sending the record outward in all directions, at the speed of light, through everything, without pause, and without preference for whether anyone is listening. Rest now. Let the numbers settle. Let the distances dissolve back into the quiet they came from. 130 million light years, 2.5 million kilometers, 11 to 13 kilometers, 1,000th the diameter of a proton. All of it, in the end, is just the universe describing itself in the only language it has ever used. And yet, the search continues, not only for the waves that have already arrived, but for the faint traces of things that may never have existed at all. cosmic strings, hypothetical creases in the fabric of spacetime itself, left over from the universe's earliest moments, have never been confirmed. No one has seen one. No instrument has yet felt the particular oscillation they would produce, but gravitational wave observations are drawing the boundaries of their possible existence ever tighter. Each new observing run places new limits on how common they could be, how massive, how long. The universe may contain them, or it may not. Either answer, in its own way, would tell us something profound. This is how science often moves, not by finding what it sought, but by learning, with increasing precision, what is not there. There is a story inside the detection of GW 15914 that is easy to overlook in the wonder of the signal itself. The signal arrived on September 14, 2015, but the world did not hear about it until February 11, 2016. 5 months passed between those two dates. 5 months of careful, methodical, almost obsessive verification. The scientists who saw the signal did not celebrate immediately. They grew quiet. They grew careful. Because they knew something that most people outside the collaboration did not. Within LIGO, a small team had the ability to inject false signals into the data. Signals designed to look exactly like real gravitational wave events. These blind injections were a way of testing the analysis pipeline, of making sure the software, the algorithms, the human judgment could correctly identify a real event when one arrived. The injections were made without telling the rest of the collaboration. The analysts would find them, study them, report them, and only afterward would the injection team reveal whether the signal had been real or planted. When GW 15914 appeared, the first question many scientists asked was not what caused this. It was, did someone put this here? That is not doubt. That is discipline. The verification process that followed was exhaustive in a way that is difficult to fully convey. Every possible source of noise was examined. Earthquakes, near and distant. Passing trucks on roads near the detectors. Electrical interference. Acoustic vibrations. Fluctuations in the laser itself. The behavior of the mirrors. The behavior of the suspension systems. The behavior of the atmosphere above each site. The two detectors are separated by roughly 3,000 kilometers. A genuine gravitational wave would arrive at both sites within milliseconds of each other, with a specific time delay that depends on the wave's direction. A local noise event would not. The signal matched, the timing matched, the waveform matched the predictions of general relativity for two merging black holes with extraordinary precision. And then the injection team was asked the question that had been waiting since September. They confirmed that no injection had been made. The signal was real. What followed was not a single moment of relief, but a long, slow settling into certainty. The statistical significance of the detection was calculated to be more than 5 sigma. In the language of physics, sigma measures how far a result sits from what pure chance would produce. 5 sigma means the probability that the signal was simply a random fluctuation in the noise, a coincidence. An artifact, nothing, is less than 1 in 3.5 million. That is not proof in the philosophical sense. Nothing in empirical science ever is, but it is as close to certainty as the discipline allows itself to come. And so, on a February morning in 2016, the world was told. The data from that detection, and from every detection since, does not belong to any single institution. It is made publicly available to any scientist anywhere in the world who wishes to examine it. The archives are open, the numbers are there, the raw strain measurements, the calibration files, the noise characterizations. This openness is not incidental. It is a considered choice. Science that cannot be checked is science that cannot be trusted. And so the universe's signals, once captured, are released. Some of the people who have searched that data are not professional physicists. Citizen science projects have brought the gravitational wave archives to anyone with curiosity and a computer. Members of the public, working through structured platforms, have helped scan the data for signals that automated systems might have missed. There is something quietly moving about that. The universe sends a ripple across 1 billion light years, It passes through the Earth in a fraction of a second, and somewhere, later, a person sitting at a desk in an ordinary room helps determine whether it was real. The tools for searching have grown more sophisticated with each passing year. Machine learning algorithms, trained on thousands of simulated signals, have become increasingly capable of finding genuine events buried in the noise. They do not tire. They do not carry assumptions about what a signal should look like. They find patterns that human analysts might overlook. This matters more with each new generation of detectors. Future instruments, with their greater sensitivity and broader reach, may detect gravitational wave events not once a month or once a week, but many times each day. The catalog that took years to build to 90 events may eventually grow by that many in a single observing run. Automated systems will handle most of the initial analysis, flagging candidates, estimating parameters, alerting astronomers to follow up with their own instruments. The universe, it seems, has been busy, and we are only now beginning to keep pace with its output. There are signals that have not yet arrived, events that have not yet happened, or that have happened but whose waves have not yet reached us. Among the most anticipated is a supernova in our own galaxy. The last one visible to the naked eye occurred in 1604, before telescopes, before any of the instruments that now watch the sky. Astronomers estimate that a supernova occurs in the Milky Way roughly once or twice per century on average. We are, by that measure, somewhat overdue. When it comes, it will be unlike anything the detectors have recorded so far. The gravitational wave signal from a collapsing stellar core would not be a clean chirp rising to a brief crescendo. It would be complex, prolonged, shaped by the turbulent, asymmetric violence of a massive star tearing itself apart from within. The signal would carry information about the convective motions inside the collapsing core, about the formation of the neutron star at its center, about the shock wave propagating outward through layers of gas that have been burning for millions of years. Current instruments could detect such a signal if the star is close enough within our galaxy, or perhaps the nearest satellite galaxies. The closer it is, the richer the signal. And it would not arrive alone. Neutrino detectors around the world would register the flood of particles released in the core collapse, arriving minutes before the light. Gravitational wave detectors would feel the asymmetric motion of the collapsing mass. Optical telescopes would watch the brightening in the sky. All of it, together, describing the same event from every angle that physics allows. That observation, when it comes, will be the most complete portrait of a dying star ever assembled. For now, the detectors wait, as they have always waited, in their long, quiet arms, listening to the geometry of space for the next thing the universe chooses to say. The last time a human being watched a star die with naked eyes alone was in the year 1604. Johannes Kepler observed it, a new light appearing in the constellation Ophiuchus, brightening over weeks, then slowly fading. He had no telescope, no detector, no way of knowing what he was truly seeing. Only that something in the sky had changed. That was the last confirmed supernova visible to the unaided eye within our own galaxy, more than 400 years ago. Since then, the instruments have come, the telescopes, the radio arrays, the neutrino tanks buried deep underground, the laser interferometers listening to the geometry of space itself. And still, no galactic supernova has arrived to greet them. Astronomers estimate one occurs roughly once or twice per century. On average, the universe is not overdue in any meaningful sense. Randomness does not work that way. But the next one is out there, somewhere in the galaxy, in a star that has not yet decided to end. When it comes, nothing like it will ever have been observed before. Every detector will turn. The gravitational wave observatories will feel the asymmetric collapse. The neutrino detectors will register the flood of particles that escapes the core in the first seconds, before even the light breaks free. The optical telescopes will watch the sky brighten over hours and days, and all of it will describe the same event, the same dying star, seen through every sense that physics has given us. That will be the most information-rich astronomical observation in human history. A single star, ending, and in its ending, teaching us more about matter and gravity and the deep interior of collapsing things than any observation that came before. For now, the detectors wait. And while they wait for that sudden, violent signal, they're also listening for something far quieter. Something continuous. There's a class of gravitational wave that does not arrive as a chirp or a burst. It does not rise and fall in a fraction of a second. Instead, it hums steadily, persistently, at a fixed frequency, like a single note held without pause. These are called continuous gravitational waves, and they would come from rotating neutron stars. A neutron star spinning hundreds of times per second is already a remarkable thing to hold in the mind. A city-sized object, denser than an atomic nucleus, turning faster than a kitchen blender. But if that neutron star is not perfectly smooth, if its surface is even slightly uneven, then as it spins, it sends a continuous ripple outward through space-time. The unevenness required is almost nothing. A mountain, by neutron star standards, might be a centimeter tall. A centimeter. On an object 20 kilometers across, that is a deformation so small it would be invisible to any instrument we could press against it. And yet, at the densities involved, even that microscopic asymmetry carries enough energy to radiate. The star would slowly lose rotational energy to these waves, spinning down, imperceptibly, over vast stretches of time. Scientists have searched for these signals, carefully, patiently, combing through the data from known pulsars, the neutron stars whose precise, clock-like pulses we can track across years and decades. They have not found them yet. But the absence is not silence. It is information. The non-detection has placed limits on how asymmetric those pulsars can be. For each one, there is now a boundary, a maximum mountain height consistent with the data. The universe has not revealed these waves, but it has allowed us to say, whatever is there, it is smaller than this. That is how science often moves. Not always through discovery, but sometimes through the quiet narrowing of what is possible. There is another kind of signal the detectors are learning to hear, one that has no single source at all. Imagine every black hole merger that has ever occurred across the entire history of the universe. Billions of them, at every distance, in every direction, overlapping and blending until no individual event can be distinguished. Their gravitational waves, arriving all at once from everywhere, would create a kind of background, a constant, low murmur beneath everything else. This is called the stochastic gravitational wave background. It is not a signal from one place or one time. It is the accumulated whisper of cosmic history. Every inspiral, every merger, every violent event that ever disturbed the geometry of space, all of it arriving together as a faint, unresolved hum. Separating this background from the noise of the instruments themselves is one of the deepest challenges facing the next generation of detectors. The hum of the universe and the hum of the machine are not so different in character, and telling them apart requires extraordinary care and extraordinary patience and detectors far more sensitive than any that exist today. The Einstein telescope, Cosmic Explorer. These future instruments are being designed, in part, for exactly this task, to hear the universe's own ambient noise and to read in it the history of everything that merged and collapsed and radiated across billions of years. All of this, the chirps, the continuous waves, the stochastic background, rests on a foundation that is itself barely a century old. Before Einstein, space was a stage, fixed, absolute, indifferent. Time moved at the same rate everywhere, for everyone, always. They were separate things, space and time. One, the container, the other, the clock. And neither of them could bend, or stretch, or carry a wave. That picture held for centuries. It felt obvious, because at the scales of ordinary life, it is very nearly true. Then, in 1915 and 1916, Einstein showed that it was not true at all. Space and time are not separate. They are woven together into a single fabric, 4 dimensions, inseparable. And that fabric is not rigid. It responds to mass and energy. It curves in the presence of matter. It stretches and compresses as objects move through it. It can carry disturbances from one place to another. Spacetime is not the stage. It is part of the story. The relationship is almost like a conversation. Mass tells spacetime how to curve, and spacetime, in turn, tells mass how to move, each shaping the other, continuously, everywhere, at every scale. And gravitational waves are what happens when that conversation becomes sudden and violent. They are not waves moving through spacetime the way sound moves through air. They are spacetime itself, moving, the fabric rippling, the geometry of the universe oscillating, stretching one direction while compressing another, passing through everything without resistance, carrying the record of whatever caused them. When the concept of spacetime was first proposed, it was a mathematical structure. Elegant, strange, difficult to visualize. It took decades before anyone could test it directly, and decades more before the instruments existed to feel its motion. The detection of gravitational waves in 2015 was not just the confirmation of a prediction. It was the moment spacetime stopped being an abstraction. It became something that could be measured, something that had touched a machine, something that had, in a very quiet and precise sense, been felt. The fabric of the universe had rippled past 2 detectors in the American landscape, and something in the geometry of space had changed by 1,000th the width of a proton, and that change had been read. All of it resting on an idea that was itself only a century old when it was finally confirmed. And in that confirmation, something closed. A loop that had been open for nearly 100 years. Einstein wrote down his equations in 1916, and from those equations came a prediction he himself was not sure the universe would honor. Gravitational waves, ripples in the geometry of space-time itself. He doubted they would ever be found. Too faint, he thought. Too small. The universe, perhaps too indifferent to our instruments. And yet the equations held. Every test that followed, from the bending of starlight around the sun to the slow decay of 2 neutron stars spiraling toward each other across decades, every single one returned the same answer. The theory was right. General relativity has now been tested across a range of scales that would have seemed almost absurd to contemplate a century ago. From careful laboratory measurements, where tiny masses are weighed against the predictions of curved space-time, all the way to the collision of 2 black holes, each dozens of times the mass of the sun, merging in a fraction of a second more than 1 billion light-years away. The theory has not flinched. Every chirp matched what the equations predicted. Every ringdown, that brief, fading oscillation as a newly formed black hole settles into stillness, ringing like a struck bell, carried exactly the frequency and decay that general relativity said it should. Every tidal signature, the subtle stretching of one neutron star by the gravity of another as they drew close, matched the predictions to within the limits of measurement. The theory has held, and yet, physicists do not believe it can hold forever. Not because the evidence has wavered, but because of what the theory does not contain. General relativity describes the very large, the curvature of space-time, the motion of planets, the merger of black holes. It is a theory of smooth geometry, of continuous fields, of space that bends gracefully under the weight of mass. Quantum mechanics describes the very small, the behavior of particles, the uncertainty woven into the fabric of matter, the strange and discontinuous nature of energy at the smallest scales. These 2 theories are each within their own domain, among the most precisely confirmed ideas in all of science. And they do not agree with each other. Not in the places where both should apply at once. At the center of a black hole, where matter is compressed to a point of infinite density, general relativity breaks down. In the first instance after the Big Bang, when the entire universe was smaller than an atom, Both theories should matter simultaneously, and neither is sufficient alone. Somewhere in that territory, the place where the very large and the very small meet, there must be a deeper theory, a theory of quantum gravity, as physicists call it, one that contains both general relativity and quantum mechanics as limiting cases, the way a more complete map contains the smaller maps drawn before it. That theory does not yet exist. It remains one of the deepest open questions in all of physics, perhaps the deepest. Decades of effort, some of the most gifted minds of the last century, entire frameworks of mathematics built from the ground up, and still the question remains open. Still the two great theories sit side by side, each correct in its own domain, each silent about the others. Some physicists hope that gravitational waves may one day offer a way in, not because current detectors can probe those extreme scales directly, but because the universe occasionally produces events violent enough to push general relativity toward its limits. A black hole merger at the very edge of what the theory can describe. A neutron-star collision where the densities involved approach the boundary of known physics. If the theory is going to show a crack, it is in places like these that the crack might first appear. So far, it has not. Every signal has come back clean. Every measurement has fallen within the bounds the theory predicted. The universe, as far as gravitational wave astronomy can currently see, continues to behave exactly as Einstein said it would. But the search continues, quietly, patiently, with instruments growing more sensitive with each passing year. And while that search unfolds, there is something else worth sitting with. Something quieter. The universe has been sending these signals for billions of years. Long before any instrument existed to receive them, long before any mind existed to wonder about them, long before the Earth itself had cooled enough to hold an ocean. Two black holes merged somewhere in the distant universe, and the ripple they produced moved outward in all directions at the speed of light. It passed through clouds of hydrogen gas that had not yet become stars. It passed through galaxies still assembling themselves from the wreckage of earlier collisions. It crossed distances so vast that the universe itself expanded measurably during the journey, stretching the space through which the wave was traveling. And it arrived here. It passed through this planet, through the rock and the ocean and the atmosphere, through every forest that ever grew on this ground, through every creature that ever moved across it, through the first soft organisms in the ancient sea, through the slow accumulation of complexity across hundreds of millions of years. None of them felt it. Not because it was not there, but because nothing in the long history of life on this planet had ever developed the means to read it. The wave carried its information faithfully, without loss, without distortion, and passed through, leaving no trace that any living thing could find. For most of cosmic history, that is how it was. The universe speaking, and no one listening. Then, on a September morning in 2015, something changed. A machine of extraordinary stillness, built in the flat landscape of Louisiana and the high desert of Washington, felt a ripple pass through it. The arms of the detector, each one 4 kilometers long, held in near-perfect vacuum, isolated from the ground by systems of extraordinary delicacy, shifted by an amount smaller than 1,000th the width of a proton. And the instruments read it. That moment is sometimes described as the opening of a new sense, as though humanity, after all, its centuries of looking at the universe through light, had suddenly developed the ability to feel it, not to see it, not to hear it in any ordinary sense, but to register, directly, the motion of space-time itself. The signal lasted less than a second. Less than 0.2 of a second. In fact, at the detectors, a brief upward sweep of frequency, a chirp, and then silence. The preparation for that moment had taken a century, from Einstein's equations in 1916, through decades of theoretical work and skepticism, and slow, careful instrument building, through the long years of construction and the longer years of refinement. through the upgrade that made the detectors 10 times more sensitive than they had been before, through the months of calibration and the years of waiting. All of it for a signal that lasted less than a heartbeat. The patience required was almost geological in its scale. And the ripple itself, the thing that finally arrived, had been traveling since long before the first complex life appeared on this planet. Since before the Cambrian, before the first fish, before the first breath of anything that would one day become us. It had been crossing the universe for 1.3 billion years, moving at the speed of light through expanding space, carrying the record of two black holes that had found each other, spiraled together, and become one. And it arrived, at last, at two quiet detectors in the American landscape. The universe does not announce itself. It simply continues, sending its signals outward in all directions, without pause, without preference, without any awareness of whether anything is listening. We built something delicate enough to listen. And in that listening, something changed, quietly, permanently, and without fanfare. What changed exactly? It is difficult to say with precision. Something shifted in the relationship between this small planet and the rest of the cosmos. Not in the cosmos itself, which continued as it always had, but in us, in what we were capable of receiving. For all of human history, we had looked at the universe. We had gathered its light, radio waves, infrared, X-rays, all of it electromagnetic, all of it a form of light. And light is extraordinary. It has carried us far, but light can be blocked. It can be absorbed by dust, scattered by gas, stopped entirely by the event horizon of a black hole. There are places in the universe that light will never leave. Gravitational waves leave those places. They pass through everything, through the dust between galaxies, through the galaxies themselves, through planets and oceans, and the soft tissue of every living thing. They do not interact. They do not pause. They simply move, carrying their information intact across whatever distance lies between the source and the listener. And so, in a sense, what changed on that September morning was this. We became capable of receiving a kind of message that had always been arriving. The universe had been speaking in this register for billions of years. Every merging pair of black holes, every pair of neutron stars spiraling toward each other, every violent rearrangement of mass at cosmic scales, all of it had been sending ripples outward, through the early universe, through the long Middle Ages of cosmic time, through the era when our sun was forming, through the era when life was learning to crawl onto land. All of it passing through. Unheard. Not because the signals were absent, but because nothing existed that was still enough, precise enough, patient enough to feel them. And then something did. Two detectors set in the quiet landscapes of Washington and Louisiana, each one along, low structure, almost unremarkable from the outside. Inside, a laser split into two beams, each traveling 4 kilometers down an evacuated tube, bouncing off mirrors polished to a smoothness that has no natural equivalent on Earth. Mirrors suspended on threads of glass finer than a human hair, isolated from the trembling of the ground by systems of extraordinary delicacy. All of it designed to detect a change in length smaller than 1,000th the diameter of a proton. A proton is itself almost incomprehensibly small. A nanometer is a billionth of a meter. A proton is roughly 1/1,000,000th of that, and LIGO was built to measure 1,000th of that proton's width. The numbers stop meaning anything at a certain point. They simply gesture toward a kind of sensitivity that has no analogy in ordinary experience. What it required was stillness. A stillness that had to be engineered, maintained, protected. The detectors had to be shielded from ocean waves breaking on distant shores, from traffic on nearby roads, from the slow settling of the ground beneath them, from thermal fluctuations in the mirrors themselves. Every source of noise had to be understood, cataloged, and quieted as much as physics allowed. And even then, the signal that arrived was barely there. less than 2/10 of a second. A soft rising tone, a chirp, a brief disturbance in the interference pattern of the laser. Something that, converted to sound, resembles a quiet thud. The kind of sound you might not notice in a room with any other noise at all. But the detectors were listening in a silence that had taken decades to build. And they heard it. The two sites registered the signal 7 milliseconds apart, the time it took the wave, traveling at the speed of light, to cross the 3,000 kilometers between them. That small delay was itself a confirmation. A random noise event would not have arrived at both detectors in that precise sequence. The wave had a direction. It had come from somewhere. From a pair of black holes, as it turned out. One roughly 29 times the mass of the Sun, the other roughly 36, orbiting each other in a final, accelerating spiral, growing closer with each revolution, radiating more and more of their energy as gravitational waves, until the last fraction of a second when they plunged together and became one. A black hole of about 62 solar masses. The missing mass, roughly 3 suns worth, had been converted entirely into the energy of that wave, released in less than a second. More energy than all the stars in the observable universe emit in that same moment. And yet what arrived here, after 1.3 billion years of travel, was a whisper. Space had stretched and compressed by that 1,000th of a proton's width. And we felt it. There is something in that fact that resists easy description. It is not quite triumph, though there was certainly that. It is something quieter, something closer to recognition. As though the universe had always been there, waiting to be heard, and we had finally grown still enough. The signal was called GW150914, a name made of numbers, clinical and precise. But the thing itself was neither clinical nor precise in its origins. It was the end of a journey that had begun when 2 black holes, formed from the collapse of ancient stars, had found each other across the darkness, had circled each other for perhaps millions of years, had drawn closer, slowly at first, then faster, then in a final rush that lasted less than a breath. And the record of that moment had traveled outward in all directions. Some of it toward us, crossing the space between galaxies, passing through the slow drift of cosmic time, arriving here, at this particular planet, at this particular moment in its history, when something on its surface had finally built the instrument to receive it. The universe does not aim its signals. It sends them everywhere, without preference. The wave that reached Louisiana and Washington also passed through every other point in space at that same expanding shell of disturbance. Most of it passed through nothing, through the vast, cold emptiness between galaxies where no detector will ever be placed. But some of it found us, and we were ready. That readiness had taken a century. From Einstein's equations in 1916, through decades of theoretical work, through the long arguments about whether detection was even possible, through the construction and the upgrades and the calibrations and the waiting. A century of preparation for a signal that lasted less than a heartbeat. There is a kind of patience in that story that feels almost inhuman, and yet it was entirely human, built from curiosity and stubbornness, and the quiet conviction that the universe had something to say, and that it was worth building something extraordinary to hear it. Now the catalog grows, event by event, chirp by chirp, each one a record of something that happened long ago and far away. Each one a small addition to what we know about how black holes form, how neutron stars die, how the universe has assembled itself over billions of years. The detectors are still listening. Right now, as you rest here, they are listening. The lasers are running. The mirrors are suspended in their careful stillness. The vacuum tubes hold their silence. And somewhere in the universe, 2 massive objects are spiraling toward each other, drawing closer with each passing moment, preparing to send another ripple outward. It will travel for a long time, perhaps millions of years, perhaps billions. And when it arrives, something here will feel it. A quiet disturbance in a beam of light. A number changing by an almost nothing amount. And we will know that somewhere, long ago, something moved.